Hello there, and welcome. Tonight, we're peeling back the layers of something invisible but everywhere. Space-time isn't just what we move through, it moves us. It hums beneath atoms, twists around planets, and collapses into black holes. It lets galaxies drift apart and photons race without aging. Every law of the universe, gravity, motion, even light, follows its subtle curves. And the more you learn, the stranger it feels. Like standing on a stage you didn't realize was moving. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. Imagine standing perfectly still, no movement, no wind, no sound, just silence. And yet, even in that stillness, you're falling, not down toward the floor or through the earth, but through something far stranger. Space-time, the invisible framework that underlies everything, is not a blank stage where the universe unfolds. It is the universe, and it responds to every presence, every mass, every motion. Right now, as you lie in bed or drift on the edge of sleep, you are sinking gently through its curves, tugged softly by the weight of the earth beneath you. But this tug is not a force in the traditional sense. It is a response, a bending, a whisper in the fabric. For centuries, we imagined space as a void and time as a ticking metronome, beating in unison across the cosmos. A grand, absolute grid. Newton saw gravity as a force pulling objects toward one another, an invisible hand reaching across emptiness. But Einstein changed that picture. He told us that gravity is not a force at all. It's geometry. What we feel as weight is simply the motion of objects following the natural paths carved out by curved space-time. When a planet moves around a star, it is not being pulled in a circle. It is rolling along a dimple in the fabric of the universe, like a marble spiraling inside a warped funnel. This fabric is not metaphor. It's measurable, predictable, and strange. When a heavy object like the sun sits in space-time, it causes a distortion, not just around it, but through it, bending both space and time. Light itself, which travels at the fastest speed allowed in the universe, must follow these curves. That's why starlight bends around galaxies, why black holes can bend the very notion of direction, and why time runs differently depending on where you stand. In the 1,970 seconds, scientists placed ultra-precise atomic clocks at the top and bottom of a tall building. They ticked at different rates. The clock closer to the Earth, deeper in its gravity, well ticked just a bit more slowly. Not metaphorically, not philosophically, actually, because time is not separate from space. It is part of the same flowing, flexible entity. And when mass curves space, it curves time as well. This means the universe doesn't just exist inside space-time, it interacts with it. Space-time bends and stretches in response to matter and matter and energy move in response to the bending. It is a feedback loop, a dance. You cannot touch one without the other responding. Even the smallest presence leaves a mark, like a boat leaving ripples behind it as it moves across a lake. And when something violent happens, a star collapsing, a black hole merger, those ripples become real. In 2015, after decades of theory and silence, scientists detected gravitational waves for the first time. Two black holes had collided over 1 billion years ago, and the resulting quake in space-time had traveled across the cosmos like a trembling in an ancient spider web. It passed through our solar system, through Earth, and through your body, stretching space in one direction, compressing it in another. You didn't feel it. No one did. The shift was smaller than the width of a proton. But the wave was real. It was measured, and it confirmed what Einstein had only imagined. Space-time is alive in a way we didn't expect. Not conscious, not breathing, but responsive, tactile. If the sun were to vanish, suddenly not fade, not explode, but simply disappear, Earth would not fly off instantly. It would continue in orbit for 8 more minutes, the same amount of time it takes light to travel from the sun to us. Because gravity doesn't act instantly. It travels, like light, like sound, like a ripple spreading outward from the source. Even distant galaxies can curve the paths of light from objects behind them, acting like lenses. Not because there's a sheet of glass in space, but because the presence of mass changes the very shape of space itself. Light always travels in straight lines, but in a curved universe, straight lines are curved too, and yet we barely notice. We walk across the Earth, fly in planes, look at the stars, and it all feels stable, fixed. But that's only because space-time cradles us so completely, so seamlessly, that we cannot feel the shift beneath us. It's like asking a fish what water is, or asking a shadow if it notices the surface it falls across. We are embedded in the fabric, shaped by it, and even made from it. Einstein's equations, the ones that describe this dynamic fabric, are beautiful, but merciless. They predict wormholes, singularities, expansion. They don't pretend to comfort us. They simply tell us how space-time responds to energy, and how energy moves in space-time. From this dance, all else emerges. This responsiveness is not limited to the vast and dramatic. Even your body, small as it is compared to planets or stars, creates a distortion in space-time. Tiny, unmeasurable, but real. A soft dip in the fabric, and if you were to move, that dip would shift with you. You are not floating on space-time, you are a part of its curvature. Every atom, every breath, participates in shaping it. That's why this isn't just physics, it's personal. Right now, as you listen, Earth is turning, the moon is circling. The solar system is gliding around the center of the galaxy at nearly 230 kilometers per second. And all of it is happening inside this flexible structure. The sun bends the orbits of the planets. The planets bend the paths of their moons. The moons pull on oceans, and time flows differently for each, depending on their motion, their mass, and their position within this strange, ever-shifting map. Sometimes, late at night, it's easy to imagine the universe as a quiet, frozen thing, stars twinkling in stillness. But the truth is far more fluid. You are surrounded by a medium that is not empty. It stretches when the universe expands. It flexes when black holes collide, and it curves so gently beneath you that you almost forget it's there. But space-time remembers. It remembers every motion, every mass, every shift. It is not passive. It is not still. It is the unseen ocean in which all things move, and like the surface of water, it is always responding softly, deeply, invisibly. Whether you feel it or not, you are being pulled downward, right now, toward your bed, your chair, the floor beneath your feet. You feel it as pressure, as weight, as the quiet force anchoring you in place. But that sensation, the pull you've known since the moment you first stood upright, is not what you think it is. Gravity, in the classical sense, doesn't exist. There is no invisible rope pulling you toward the earth. No mysterious hand yanking apples from trees. What you feel is not a force at all. It is the shape of space-time telling you where to go. And like everything with mass, you are simply following the curve. Isaac Newton imagined gravity as an attraction. Masses reached out across empty space and tugged at one another with a strength proportional to their size and inversely proportional to the square of the distance between them. It worked. For centuries, Newton's equations could predict the orbits of planets, the fall of objects, the arc of cannonballs. They described how gravity behaves, but not what it is. There was still a ghost in the machine, an invisible actor making things move. Then Einstein arrived, and what he saw changed the universe. In 1915, Albert Einstein presented his general theory of relativity, a framework that didn't just update Newton, it dismantled the entire foundation. According to Einstein, mass doesn't reach out. It bends. The presence of mass and energy curves the fabric of space-time itself, and objects moving through that space aren't pulled, they're guided. Like marbles rolling along the inside of a warped bowl, they follow the straightest possible paths available to them. Only those paths are curved. The Earth doesn't orbit the sun because it's being yanked around. It's orbiting because the sun has reshaped the space around it, and the Earth is simply falling along the contour. This idea is hard to feel. We're used to thinking in lines and forces, not in curves and geodesics. But imagine a trampoline stretched tight. If you place a bowling ball in the center, the fabric sinks. Drop a marble nearby, and it will spiral inward, not because the bowling ball is pulling it, but because the surface it rolls on has changed shape. That's a two-dimensional analogy, of course, but in our three-dimensional universe, space warps in every direction. Time does too. And this warping is not metaphorical. It's measurable. Astronomers have watched starlight bend as it passes behind massive galaxies. We've observed time stretch and slow near black holes. We've launched satellites that must constantly correct for the tiny distortions in time caused by Earth's gravitational field, because GPS won't work without those relativistic adjustments. The universe doesn't just respond to mass, it reshapes itself in its presence. Geometry becomes destiny. On the surface of Earth, you stand on a planet that has curved space-time around itself like a dip in calm water. You are not held down by an invisible force. You are prevented from moving in the direction space-time wants you to go downward, inward, through the curvature. When you jump, you follow a brief arc. When you fall, you follow a longer one. And when an object is dropped, it takes the most natural path available in that curved geometry. The only reason you don't feel weightless is because the ground pushes back. Even black holes, those mysterious voids of nothingness, are not defined by force, but by shape. A black hole is a region where the curvature of space-time has become so steep, so extreme, that every possible path leads inward. Light itself cannot escape, not because it is being pulled, but because every straight line it could travel has been redirected toward the center. Gravity has not strengthened, space has deepened. This shift in thinking doesn't just change how we view motion, it changes how we view existence. Because if gravity is geometry, then the universe is not filled with objects acting on each other from a distance. Instead, it is a smooth, connected whole, an unbroken surface with dimples, folds, and undulations created by everything that exists. Planets, stars, galaxies, all of them are shaping the very space they move through. The result is not a war zone of competing poles, but a vast and elegant flow of curvature and motion. Every orbit is a story told in curves. On the moon, where the mass is smaller, the dip in space-time is shallower. You float a little farther, fall a little slower. On Jupiter, where the mass is enormous, the curvature steepens. Time itself moves more slowly there. This isn't theory, it's physics, real and tested, over and over. Clocks tick at different rates depending on how close they are to mass. Particles spiral differently depending on the curve they trace. And in the farthest reaches of the universe, galaxies distort the light behind them, revealing invisible shapes through gravitational lensing shapes, etched not by force, but by form. It's easy to imagine a flat universe, a grid where things move according to rules. But that's not what the cosmos has given us. We live in a contoured reality, a sculpture too vast to see all at once. And in that sculpture, your body presses downward not because Earth commands it, but because that is the shape your motion must take, even as you lie. Still, you are being guided by geometry, sinking along the curvature of space-time, nudged gently by the shape of what surrounds you. This is the quiet truth Einstein uncovered, that the universe is not a stage upon which things act, but a living diagram of interactions, molded by every star and speck of matter. Gravity does not call out, it listens, and then responds with a curve. And everything else, motion, orbit, fall, flow, is simply the result of moving through that curved space in the only way possible. In this way, the universe is graceful, not in its simplicity, but in its coherence. In a cosmos made of curves, every path is part of the pattern, and the weight you feel right now, the pull that tethers you to your bed, is not a chain or a force or a reach. It is the shape of the world wrapping around you. You are not being held. You are moving as space-time tells you to move, gently, inevitably, naturally. Time feels constant. It ticks in regular beats, one moment after the next, like water dripping in a still room. You live by it. You measure your days, your years, your memories by its rhythm. But time is not fixed. It flows at different speeds depending on where you are and how fast you're moving. And though you may not feel it, your body has always existed inside this strange, shifting current. Even now, lying in bed or walking down a hallway, time is passing faster at your head than it is at your feet. Not by much, just a few billionths of a second per year, but it's enough. Gravity bends not just space, but time. And the deeper you are in a gravitational field, the slower time flows. Your feet, being slightly closer to the center of Earth's mass, experience a fraction more gravity than your head, so they age more slowly. So do valleys compared to mountaintops. The ground itself, under more pressure from the planet's weight, ticks a tiny bit behind the sky. Astronauts experience this difference in an even stranger way. While They orbit Earth at great speed. They are also slightly farther from its gravitational pull. Velocity slows time down. Distance from gravity speeds it up. These two effects pull in opposite directions. But depending on the altitude and speed of the orbit, they don't cancel out perfectly. For those aboard the International Space Station, time slows just enough that when they return to Earth, they are younger by milliseconds than they would have been had they stayed home. It's not science fiction. It's relativity. This phenomenon, called time dilation, is not some exotic edge case. It's embedded in the structure of the universe. The faster you move through space, the slower you move through time. A person racing near the speed of light would find time dragging behind them like molasses, while someone watching from a stationary point would see that same person's clock nearly frozen. If you could somehow travel fast enough, you could cross a galaxy in a few days. While millions of years passed outside your ship, you would return home to find everyone you knew to long gone. The world unfamiliar, the Earth changed. You would be younger, but everything else would be old. It's hard to feel this difference in daily life. You live within Earth's gentle gravity, moving at human speeds, and time feels stable here. But every GPS satellite orbiting above you has to account for time dilation. Their onboard clocks tick differently than those on the ground, faster due to weaker gravity, slower due to higher speed. If the system didn't correct for this imbalance, your phone would drift off by kilometers every single day. Time is elastic, and technology must bend with it to remain accurate. This was one of Einstein's most unsettling insights, that time is not absolute. There is no single ticking clock shared by the universe. Instead, each point in space-time has its own version of time's flow, shaped by motion, gravity, and position. The more you resist gravity by standing taller, by climbing higher the faster your seconds move, the more you race forward on a plane, in orbit the slower they pass. Every observer has their own tempo, their own unfolding of events. That means there is no universal now. Two people far apart, moving at different speeds, may disagree about which events are simultaneous. The universe doesn't care. It allows both perspectives to be real. Time, like space, is woven into a flexible, relative whole. It can bend, it can stretch, it can slow to a crawl, or race forward, depending on how you move within it. And so, over the course of your life, you've aged differently from others without ever noticing. You've lived through seconds that lasted longer, and seconds that passed more quickly, all depending on the paths you've taken. If you've flown across oceans, your time stretched. If you've stood atop mountains, you've aged just a little more than those at sea level. Even the beating of your heart rising and falling as you sleep or run shapes your journey through time in imperceptible ways. It's not a flaw in perception. It's not a trick. It is the fabric of reality unfolding beneath your feet. And when you look at the stars, those ancient lights scattered across the sky, you're seeing time itself delayed. A star 10,000 light years away is not just far in space, it's far in time. You are looking at it as it was, not as it is. And if someone near that star were looking back at you, they wouldn't see your present. They'd see a younger Earth, dinosaurs, perhaps, or the early rustle of life. We live in a universe where time is not a river flowing from past to future, the same for all who sail it. It is a landscape, a terrain, with hills and valleys and stretches where the seconds pool and stretch thin. You carry a clock in your chest and another in your mind, but neither ticks in harmony with the stars or even the people beside you. Time moves differently for everyone, and in those tiny differences, those slippages, those subtle elongations lie the mysteries of what it means to exist. When you look up at the night sky, it's easy to imagine the stars and galaxies as still, suspended like lanterns in a vast and silent dome. The darkness between them seems empty, a void that separates one island of light from another. But the space between those islands is not still. It's not even static. It's growing, quietly, invisibly, relentlessly. Not because the galaxies are drifting apart like boats on a calm sea, but because the sea itself is swelling beneath them. Space-time, the fabric of the universe, is stretching. Not at the edges, not from some central explosion, but everywhere, all at once. Between galaxies, between clusters, between the very atoms that make up the cosmos. The expansion doesn't push things outward. It creates more of space in between them, and the objects that once sat close together now find themselves farther apart, not because they moved, but because the ground beneath them changed shape. This idea sounds impossible at first. In our everyday world, movement implies velocity, force, momentum. But on a cosmic scale, it's not movement that carries galaxies apart. It's the expansion of the medium itself. Imagine baking a raisin-filled loaf of bread. As it rises, the dough stretches, and each raisin moves away from the others. Not because they are crawling outward, but because the dough is expanding between them. That's what space is doing. The galaxies are the raisins. The universe is the dough, and this expansion is not slow. In the vast stretches between galaxies, space is growing at a rate so rapid that some objects are being carried away from us faster than the speed of light. That doesn't break the rules of physics, because the galaxies themselves aren't moving through space faster than light. It's the space between us that is expanding. Light is still the ultimate speed limit for objects with mass traveling through space. But space itself? It has no such limit. The evidence for this came in the form of redshift. When astronomers looked at distant galaxies, they noticed that their light was shifted toward the red end of the spectrum. Not just some galaxies, all of them. The farther away they were, the more redshifted their light became. At first, this was interpreted as Doppler motion, like the sound of a siren lowering in pitch as it speeds away. But the better explanation, the one that fit the data more elegantly, was that the light itself was being stretched along with space. Photons released billions of years ago have been riding the expanding universe ever since, their wavelengths pulled longer by the very fabric they travel through. And the implications of this are profound. It means the universe had a beginning, a moment when space itself was condensed into something unimaginably dense and hot. Not an explosion into space, but an explosion of space. The Big Bang wasn't a point in the void, it was the moment the void began, and it never stopped. The expansion has continued for 13.8 billion years, turning a fireball of energy into a tapestry of galaxies, stars, and dust. But the most startling revelation came much later. Scientists once believed that gravity, the great attractor, would eventually slow this expansion, maybe even reverse it. A universe that stretched, then stopped, then collapsed back into itself. But in 1998, observations of distant supernovae showed something unexpected. The expansion wasn't slowing down, it was speeding up. Some unknown pressure was pushing space apart faster and faster. This repulsive energy was dubbed dark energy, not because it is dark, but because it remains unseen and poorly understood. Whatever it is, it now dominates the universe. Not stars, not galaxies, not matter, but this strange, accelerating force that causes space-time to stretch more and more with each passing moment. In billions of years, galaxies that are visible to us now will disappear beyond our cosmic horizon, not because their light has dimmed, but because the space between us has grown so vast that their light can no longer reach us. They will slip beyond the edge of visibility, like ships sailing over a curve we can never cross. The universe will feel more empty, not because it has lost anything, but because distance itself has grown too large to bridge, and still, the expansion will continue. This isn't something we feel. The space between you and your pillow isn't stretching. The space inside atoms is held tight by forces far stronger than dark energy. Even galaxies and clusters of galaxies are bound by their own gravity. It's only in the vast, quiet gulfs between the structures of the cosmos that expansion takes hold. It pulls not with force, but with inevitability. There's no center, no edge, just a smooth, continuous stretching of the stage we stand on. The scale of it is hard to grasp. Every second, millions of kilometers of new space bloom into existence, not from a source, not from emptiness, but from the rules baked into the universe itself. A gentle, accelerating swell. And in that swell, every photon, every wave of light, every footprint in time is carried outward, away from its origin. The universe is not just expanding, it is expanding faster. Each moment builds on the last. Each stretch gives rise to the next, like a breath that never ends. And in that breath, we are cradled, not drifting on the surface, but expanding with it, embedded in it, riding the curves of a reality that is still unfolding. So when you stare into the sky and feel the pull of distance, know that it's not just far, it's growing. And what you see now, these stars, these galaxies, this glimpse into the ancient past, is already on its way to somewhere unreachable. The night sky is not a window. It's a memory of light from places being slowly carried away. not by motion, but by the quiet, invisible stretch of space-time itself. Close your eyes and think about this moment. The sound of your breath, the soft hum of whatever surrounds you, the gentle beat of your heart. It feels real, anchored in the present. You are here, now. But in the universe, now is not a universal truth. It's not a thread that wraps everything together in perfect synchronicity. It's a perspective, personal, local, and shaped by your motion through space-time. What feels like the present to you may already be the past to someone else, or a moment not yet come. There is no shared heartbeat across the cosmos. Just countless rhythms, each unfolding in its own frame. Einstein's theory of relativity broke time away from its pedestal. It showed us that simultaneity, two events happening at the same time, is not absolute. It depends entirely on your vantage point. Imagine two lightning strikes hitting opposite ends of a train track, to someone standing halfway between them. The flashes might appear to happen simultaneously, but to a person riding on a fast-moving train, passing through the same scene, the light from one side will reach them before the other. To them, the strikes did not happen at the same time, and both observers would be right. Time, it turns out, is not a single thread stretched tight across the universe. It's a web of threads, each with its own twist. This realization changes everything. It means there is no single, universal moment that can be said to be happening right now everywhere. Your now is not the same as mine if I'm in motion, or if I'm deep in gravity, or simply far away. In space-time, each observer carves their own slice of the universe, what's happening, what has happened, what's yet to happen, and those slices tilt and shift depending on their speed and their location. The faster you move, the more the universe tilts. A clock in your hand still ticks normally, but compared to someone standing still, your version of now slides. On Earth, we don't notice. Our motions are slow. The gravity we live in is mild. But stretch that idea across light years, across galaxies, and the illusion of simultaneity falls apart completely. A star exploding in a far-off galaxy might be happening now in your frame, already over in mine, and yet to occur in someone else's. Time, in this sense, is not something we all swim through together. It is something we each shape by the way we move. And this leads to a haunting thought. If the present is relative, then what does that say about the past and the future? If my now includes events you haven't experienced yet, and your now includes moments I've already seen, then maybe all those moments still exist. Not just in memory or potential, but as real as the one you're in right now. The idea that the past has vanished and the future is unwritten may only be a trick of consciousness. The universe doesn't delete old frames or wait to paint new ones. They're all still out there, stacked, layered, silent. Physicists call this the block universe, a vision of space-time, where all moments, past, present, and future, coexist. Where time doesn't flow like a river, but exists like a landscape. You don't walk through it, you are part of it. Your life, every second of it, already etched into the fabric. From your first breath to your final blink, the whole path is there, like a thread frozen in ice. The illusion of movement is just the way your mind processes the frames. In this view, the universe is not changing. We are simply moving along our own world lines, experiencing one cross-section of reality at a time. The now, you feel, is just a slice thin and temporary, but behind you, nothing is lost. Ahead of you, nothing is uncertain. It is only your awareness that hasn't arrived there yet. This doesn't mean we're trapped. It doesn't mean fate has chained every moment, but it does suggest that time is far stranger than we ever imagined. We do not live at the center of a universal moment. We live on a timeline that intersects with countless others, each with its own present, each with its own direction. And in this network of perspectives, the very idea of a shared now dissolves. If someone traveled far enough away, moving fast enough in the right direction, they could shift their now to include events from your future, not by magic, not by guessing, but because motion itself reorients time. To them, something you haven't yet experienced could already be part of the present, and to someone else, that same event is long gone. Time, like space, is subject to perspective, and from that perspective, the universe becomes a place not of things happening, but of things already existing, waiting to be seen from the right angle. The stars you see in the sky are old. That's not a poetic metaphor, it's literal. You're seeing them as they were. The light reaching your eyes tonight left its source years, centuries, even millennia ago. Some of those stars are gone. Their light is still coming, which means your present includes the pasts of distant places, just as someone far away might one day see the light from our present long after we've moved on. This is the quiet paradox of time in the universe. You are always in the present, but the present is not always the same for everyone. It's a drifting window through a vast architecture of moments, and we each carry our own. There is no master clock, no single heartbeat counting the seconds for all things. Just your time, your motion, your now. And yet, even knowing this, you return to the moment, to your breath, to the soft texture of now. Not because it is the only one that exists, but because it is the one you're in, a fragile flicker, balanced on the edge of memory and possibility, glowing quietly in the dark. Somewhere out there, in the silent folds of space, lie the broken places. Not broken in the way of shattered glass or crumbled stone, but broken in the deeper sense where the rules of the universe stop working the way we expect, where space bends too far, and time twists into something unrecognizable. These are black holes. Not holes in the sense of absence, but rather places so full, so dense, that they become prisons of their own gravity. Gravity not as a force, but as a pit so deep that even light, the fastest thing in existence, cannot climb out. A black hole begins with collapse. A massive star burns for millions of years, fusing hydrogen into heavier elements, holding itself up by the pressure of its own light. But eventually, it runs out of fuel. The light falters, the balance tips, and gravity wins. The star implodes, its core crushed tighter and tighter, until nothing can resist the inward pull. It becomes a singularity, a point of infinite density, hidden behind a veil known as the event horizon. The event horizon is not a surface. You could not land on it or touch it. It is a boundary defined not by substance but by consequence. Once crossed, there is no way back. No signal, no particle, no flicker of light can escape. From the outside, it appears as a sphere of perfect darkness. Not because there is nothing there, but because everything there is cut off from us forever. This edge is a one-way gate. You could pass through it without noticing. If you were floating toward a black hole, you might feel nothing at all as you slipped past the horizon. No jolt, no shimmer, just a point beyond which the path forward is absolute. There is no turning around. The space you fall into has curved so steeply that all roads lead inward. Even light, which usually races in straight lines, is bent back on itself like a tethered thread. The black hole doesn't pull light in, it gives light no direction left to go. From the outside, time near the horizon appears to slow. A person falling toward a black hole would seem to freeze in place as they approached it, their final moments stretching endlessly into the future. But from their own perspective, time would march on as usual. They would pass the boundary and continue falling, helpless, toward the singularity at the core. What lies there, no one truly knows. It is a place where our understanding breaks. Equations spit out infinities. The geometry of space-time folds so violently that it ceases to resemble anything we can measure or predict. It's tempting to think of black holes as rare anomalies, scattered here and there. But they are not rare. At the heart of nearly every galaxy, including our own, spins a supermassive black hole, millions or even billions of times the mass of our sun. These giants anchor galaxies, shaping their rotation, influencing their growth. Without them, the spiral arms of stars might never have formed. Without them, perhaps we would not be here at all. And yet, they remain hidden. Not because they are small, but because they offer nothing back. No light, no surface to reflect from. They can only be seen by their effects, the way they tug on nearby stars, the way they bend and warp the light that passes close. In 2019, humanity caught its first glimpse of one, not directly, but as a glowing ring of gas and plasma spiraling toward the void, heated to incandescence just before being lost forever. The center of that ring? Pure black. Black holes distort not just space and time, but our sense of causality itself. Inside the event horizon, the roles of time and space can reverse. Time, which once flowed forward, becomes a direction you cannot escape. It carries you inward, like a current too strong to swim against. You do not fall because you are pushed. You fall because the very structure of space-time has no other direction left to give you. And still, these are not places of violence from the inside. A sufficiently massive black hole would stretch your body gently as you entered. The gravitational difference across your height spread so thin that you might never notice. But a smaller one? That's another story. The gravity changes so rapidly over short distances that it pulls more strongly on your feet than your head, stretching you into a long, thin thread. Scientists call this spaghettification, a poetic horror, a quiet undoing. There are theories that black holes evaporate over time, leaking tiny amounts of energy through quantum effects, a process called Hawking radiation. If true, it means black holes are not eternal. They fade, slowly, over trillions of years. But for now, they are the most permanent things we know. Silent, patient, waiting in the dark. Some even wonder if black holes are more than graves, that perhaps, in their hearts, they hold doorways, that the singularity, rather than being the end of space-time, is a bridge to something else entirely. A white hole, a new universe, a restart. These are speculations, beautiful, terrifying, but still beyond the reach of evidence. For now, the horizon remains closed. But even without certainty, black holes whisper something profound, that the universe has limits, that even light, which can circle galaxies and cross the cosmos, has places it cannot return from. That gravity, under the right conditions, can carve holes not in space, but in the structure of reality itself. And somewhere out there, one of those holes is watching, invisible, unmoving, a place where time itself goes to end. A broken place, not because it is damaged, but because it is too complete. A silence too deep to escape. A secret kept not by choice, but by the nature of the universe itself. You lie still. The room is quiet. Perhaps there's a soft hum in the distance, the rise and fall of your breath, the weight of the blanket draped across your chest. It feels like rest, like stillness. But you are not still, not even close. At this very moment, you are flying, spinning, falling, hurtling through a universe that never stops moving. The ground beneath you is not fixed. It's moving too, pulled along a curved path by forces you do not feel and shapes you cannot see. Stillness, it turns out, is a trick of perception. The calm is real, but the quiet is not the same as being still. Begin with the most familiar. Earth rotates on its axis at roughly 1,000 miles per hour at the equator. You don't feel it. The air moves with you. The trees, the oceans, the sky. There's no wind from it, no blur. But the surface of the planet is sweeping eastward in a steady, relentless spin. Above you, stars seem to rise and set, but they're not moving, you are. The sun arcs across the sky, not because it circles you, but because your planet is turning, again and again, like a cradle rocking in slow motion. But the spin is only the beginning. Earth itself is on a journey. It orbits the sun at about 67,000 miles per hour, making a full revolution every 365 days. The seasons, the constellations, the tilt of light across your window, they are all expressions of this orbit. You are being carried through space at speeds faster than any jet or rocket, your body looping endlessly through the gravitational well of a nearby star. And yet, you feel no wind in your face, no pressure pulling you backward. Motion becomes invisible when everything around you shares the same speed, and it doesn't stop there. The sun, that brilliant centerpiece of our solar system, is also in motion, dragging all its planets and moons and asteroids along in a great spiral through the Milky Way. Our galaxy is not static. It's a swirling disk of hundreds of billions of stars, each with its own motion, each orbiting the galactic center in a slow, majestic dance. The sun takes about 230 million years to make a single trip around the galaxy. You are aboard that voyage, too, riding through its arms like a passenger on a vast, invisible train. Even the galaxy is not fixed. The Milky Way itself is moving, pulled by the gravity of other galaxies, by the distribution of dark matter, by the warping of space-time on scales almost too large to name. Our entire local group of galaxies is falling toward something, toward the Virgo cluster, toward the even more massive Laniakea supercluster, and perhaps toward a deeper mystery still, the Great Attractor, a gravitational anomaly so massive that galaxies tens of millions of light years away are drifting toward it like leaves on a cosmic tide. All of this motion, all of this momentum, and you feel none of it. Not because it isn't real, but because you are part of the system. You move with the Earth, with the sun, with the galaxy. The same way a person on a train feels still while the landscape blurs by. The same way water in a glass stays level as the airplane cruises through the sky. Motion is only noticed when there's resistance. And in space, there is no air, no friction, no edge to push against. The whole universe is in motion, and you are flowing with it. Even down at the level of atoms, motion never stops. The particles in your body vibrate, shift, rotate. Electrons swirl around nuclei. Quarks pulse within protons and neutrons. There is no true rest, no perfect pause. Absolute zero, the temperature at which motion would cease, is unreachable. Everything, everywhere, is dancing. And because space-time itself is curved, your motion is not a straight line. You are falling, constantly. Earth's orbit around the sun is a fall that never ends. Gravity bends space, and objects follow the curve. That's what orbits are, not circles of force, but paths of surrender. The moon falls around the earth falls around the sun falls through the galaxy, and you, tucked inside this chain of motion, are falling too. You fall through space-time every second of your life, pulled not by ropes or winds, but by the shape of the cosmos itself. You may sit still on a chair, you may lie still in bed, but beneath that stillness is a cascade of movement, each layer built upon the one before it, rotating, orbiting, spiraling, drifting, from the atomic to the galactic, from the quiet rhythm of your heart to the cold sweep of stars across the void. Nothing stands still. It's humbling, and it's beautiful, because it means that no part of you is ever separate from the cosmos. You are embedded in its flow. You are a participant in its motion. You belong to it, and it carries you forward, second by second, across the deepening dark. There is no fixed center, no unmoving frame. The universe does not offer a platform outside itself where stillness can be measured. Every motion is relative to something else, and every something else is already moving. Stillness is always a matter of comparison, and when everything moves, there is no absolute rest. So next time, you pause. Next time you close your eyes and let the day slip away, remember that you are not truly still. You are soaring through space, through time, through a universe that never stops unfolding. And maybe that's what makes rest so precious, not because it stops the motion, but because it lets you feel it quietly, like a song played in the background of all things. The silence of your room is a shell. Inside it, a galaxy turns, a star hurtles, a planet spins, and you soft, breathing, waiting, are part of it all, always in motion, even when you forget. In the vast and intricate machinery of the universe, there is a speed beyond which nothing can go. It is not a suggestion or a preference. It is a boundary etched into the fabric of reality itself. The speed of light, 299,792,458 meters per second, is more than just how fast light travels. It is the universe's ultimate speed limit, the fastest that information, energy, or cause and effect can ever move. And though you may never feel it in your daily life, this speed governs everything you see, everything you know, everything that can ever touch or shape your world. Light is not the only thing that travels at this limit. Gravitational waves, the trembling of space-time itself, move at this speed. So do the electromagnetic pulses that let atoms talk to one another. But nothing with mass, nothing with substance, can reach it. The closer something with mass tries to get to this barrier, the more energy it takes, and the effort increases steeply, cruelly, until it becomes infinite. A particle accelerated faster and faster approaches the speed of light, but never quite gets there. It is a ceiling that cannot be broken, a rule without exceptions. The strange part is that light's speed is not relative. It doesn't matter how fast you're moving when you try to measure it. Whether you're standing still, speeding forward, or rushing in the opposite direction, you will always measure light's speed as the known. Same. This constancy defies intuition. Most things in motion look different depending on your own motion. But light plays by different rules, and it is those rules that forced us to rewrite our understanding of time and space. Einstein realized that if the speed of light is always the same, then space and time must be flexible. They must stretch and compress to keep that speed unchanged. This is why time slows down the faster you move. It's why lengths contract. It's why simultaneity breaks apart. All to protect this sacred limit, to ensure that light never appears to change speed, no matter how you chase or flee from it. Because of this limit, we live in a world of delay. You never see the universe as it is, only as it was. The light from the moon takes over a second to reach you. The light from the sun takes more than 8 minutes. Even the light from your friend's face, sitting across the room, takes a fleeting fraction of a second to arrive. Not noticeable, not perceptible, but real. Reality is always arriving late. Every glance is a message from the past. The further out you look, the deeper into history you peer. Galaxies seen through telescopes are not the galaxies of today. They are ancient portraits, messengers from millions or billions of years ago. You can never see a galaxy as it is now, because the light that would show you that has not yet arrived. And it may never. The speed of light, fast as it is still finite. And in a universe that is expanding, some things are already too far for their light to ever catch up. This speed limit defines the edges of our knowable universe. There are places, right now, whose light will never reach us, not because they are hidden, but because the distance is growing faster than light can cross it. These regions may be teeming with stars, with life, with entire histories of their own. But to us, they are invisible. Not because we lack the tools to see them, but because causality itself forbids it. The same limit preserves order. If information could travel faster than light, events could happen before their causes. Time could unravel. Messages could arrive before they were sent. The future could reach back into the past. The arrow of time would lose its point. But because light's speed is firm, effects always follow causes. Time flows forward. Stories make sense. The cosmos has a rhythm we can trust. And in a way, this boundary gives the universe shape. It defines what can influence what. It carves out regions of potential, where events are linked, where things can touch, collide, speak. The rest, the places beyond, exist too, but are unreachable. The cosmic speed limit draws a line between what is connected and what is forever separate. You live well below this limit. Even the fastest spacecraft humanity has ever launched move at only a tiny fraction of light speed. But the effects still reach you. GPS satellites must account for the fact that time ticks differently at their speeds. Particle accelerators must wrestle with relativistic mass. And your own body, right now, is aging ever so slightly differently depending on your motion through space and the strength of gravity holding you to the Earth. The speed of light is not something out there. It shapes the texture of your every moment. And yet, light is not infinite. It is not instantaneous. It takes time to arrive, to reveal, to touch. If the sun vanished this instant, you would not know for 8 minutes. The Earth would keep orbiting, blind to its loss, until the final rays arrived. That delay, that quiet pause between reality and realization, is a fundamental truth of our existence. The world is always a step ahead of your awareness. But perhaps there is something beautiful in that. The idea that what you see is always a gift from the past. That the stars in the sky are still speaking long after their voices have gone silent. That even the light bouncing off your own hand took time to reach your eyes. Every vision, every shimmer, every reflection, an echo, a delay. A reminder that the universe is vast and that the journey even of light is not without cost. So much of what we know rides on that speed. It is not a flaw or a limit to be broken. It is a law that brings coherence, a thread that binds space and time into one fabric. The speed of light is not just how fast things can go. It is how the universe holds itself together. And as you sit in the quiet, wrapped in stillness, remember that you are surrounded by light still on its way. Some just left a lamp across the room. Some is coming from a star that died before life on Earth began. But all of it travels at the same pace, crossing the dark, obeying the same rule, weaving time into a single unfolding story, one beam at a time, high in the mountains, where the air thins and the stars feel just a little closer. Time ticks a little faster than it does at sea level, not by much fractions of a second spread across years, but it's real, measurable. And as you descend back toward valleys, oceans, cities built low on the land, time slows again. Not because of clocks or human perception, but because gravity itself bends the passage of time. Where gravity grows stronger, time grows quieter. Each second stretches, each moment lingers. And though we rarely feel it, this gentle warping surrounds us always. Gravitational time dilation is one of the more unsettling consequences of Einstein's theory of general relativity. The idea that space can bend was strange enough. But time, the very rhythm that orders thought and memory, heartbeat and breath, to imagine that it can be stretched and slowed by the presence of mass that was something deeper, more personal. It begins with the understanding that gravity isn't a force pulling objects down, but a curve in space-time, a dent in the fabric of reality caused by mass and energy. And time, being part of that fabric, is affected too. Near massive objects, planets, stars, black holes, the curve deepens, and inside that curve, time slows. It's not metaphor, it's not perception, it's not about how things feel, it's real. Atomic clocks placed at the bottom of a tall building tick just a bit more slowly than those at the top. If you lived on the first floor and your twin lived on the rooftop, and you compared notes after a few decades, you would have aged just a little less. Not enough to notice, but enough for physics to know. Enough for satellites to compensate for when guiding GPS signals across the sky. This isn't some obscure curiosity. It's woven into our technology, our communications, our understanding of the world. The devices that help planes land, that map cities, that let you navigate to a friend's house or find your way home, they must all account for the subtle shift in time caused by Earth's gravity. Without this correction, your GPS would drift by miles each day, and the effect grows, more intense with more mass. Near a neutron star, time slows dramatically. A single second might pass for you while years slip by far away. Near a black hole, the effect becomes extreme. At the event horizon, time appears to stop entirely frozen, suspended. From the outside, anything falling in seems to slow to a halt, caught in a kind of eternal pause. But from the perspective of the falling object, time continues normally. It's the rest of the universe that seems to rush ahead. This paradox that time is both normal and distorted depending on your point of view is one of the more haunting truths of the cosmos. Two people can experience wildly different flows of time simply because of where they are in the curve of gravity. One might live a moment, the other a century. And it's not just the extremes that matter. Even here, on Earth, the slow drag of gravity shapes the tempo of every life. A second on the surface is not the same as a second in orbit. Time runs just a little slower for those held tighter by gravity's pull. Mountains rise, valleys sink, and time responds in kind, flowing just a little more quickly in the high places, just a little more slowly in the deep. This effect is not something you can escape. Mass bends space-time, and time obeys. It stretches near anything heavy, anything dense, anything real. Every planet carries this lullaby of slowness. Every star sings it. Every galaxy hums with it. And we, small and brief and always falling through curved space-time, are caught in the rhythm. Even the Earth, gentle and familiar, is a conductor of this slowdown. The deeper underground you go, the more the curve tightens. In deep mines, in underground laboratories, time ticks fractionally slower than above. Not because clocks are faulty, but because they are obeying the shape of the world. It's easy to forget that time is not fixed, that it is not a single river we all drift down together. Time is sculpted by the world around it, bent by weight, by depth, by gravity. In a universe where nothing is truly still and nothing is truly flat, time is always folding, always stretching, always slipping in and out of sync. And so the mountain climber ages just a bit more than the sailor. The astronaut aboard the International Space Station, caught between the speed of orbit and the gravity of Earth, returns to us just a whisper younger than when they left. Every journey through curved space is a journey through bent time. Every moment carries its own weight, its own delay, its own slight tilt away from what we once believed was universal. Perhaps it's humbling. Perhaps it's poetic. That time, the most constant thing we thought we knew, turns out to be elastic. That gravity, which we once imagined simply as a pull, is also a sculptor of time itself. That even standing still, you are being shaped by invisible curves, aging a little differently than someone else, simply because of where you are. And so, under starlight or daylight, above the sea or below the earth, you are always dancing with time's quiet distortions. You are never exactly where you were a moment ago, not just in space, but in tempo, in rhythm, in the shape of time's unfolding. You are not alone in this. Every object, every star, every pulse of light, every distant echo across the galaxy feels the same soft bending. The universe is not just expanding, it is warping, breathing, And in the presence of mass, it slows its own heartbeat. Time bends, and we bend with it. There is a boundary to what we can know, a soft edge not of space, but of time, drawn not in light, but in silence. A horizon that does not sit around our planet, or our star, or even our galaxy, but one that surrounds the entire observable universe. Beyond it, galaxies drift further and faster, their light trying desperately to reach us across an ever-growing gulf. But space itself stretches too quickly. The gap widens faster than light can cross it. And so, that light will never arrive. Those galaxies are lost to us not because they vanished, but because the universe's expansion has outrun their voices. This boundary is known as the cosmic event horizon, and it marks the limit of what can ever influence us. Not just now, but ever, no matter how far we wait, or how powerful our telescopes become. There are regions of space forever beyond our reach, places where stars may still burn, where planets may orbit and life may dream, but whose light will never touch our eyes. Because that light, no matter how fast it travels, cannot catch up to the accelerating stretch of space between us. It's a strange thought that distance alone is not what separates us, but the speed at which the space in between is growing. The universe, as it turns out, is not simply filled with galaxies floating in still waters. The ocean itself is expanding. Every second, more space is created, and the more distant an object is, the faster it recedes. Not because it's moving through space, but because space itself is blooming like rising dough, like a balloon in slow and silent inflation. This expansion is not uniform in feeling. We do not see it between you and the lamp beside your bed, or between cities on Earth. Gravity holds those things tightly together, but across the vast and nearly empty reaches between galaxy clusters, the expansion reigns, and over great enough distances, it dominates. Light, fast as it is, has a limit, and when space stretches faster than light can travel, that light is pulled into an eternal race it can never win. The edge defined by this race is not a wall, and it's not fixed. It is a moving target, a consequence of how the universe evolves. When the cosmos was younger, smaller, and expanding more slowly, more regions lay within our future sight. But now, as expansion accelerates due to dark energy and invisible pressure woven into the vacuum itself, the horizon closes in, not in distance, but in potential. More and more galaxies slip beyond our grasp each year, not falling away in space, but in possibility. Their future influence, like their future light, is sealed off forever. This means there are galaxies we can still see today, their light just now arriving after billions of years of travel, whispering stories from a younger cosmos. But if we wait too long, those stories will end. Their light will no longer reach us. The next chapter will be unwritten in our sky, not because the galaxy stopped emitting light, but because the light was sent too late. We are seeing only the last rays that made it through before the horizon closed behind them. And this is not just about light. It's about causality, about connection. If a galaxy lies beyond the event horizon, we cannot reach it. No ship we build, no message we send, no probe or beacon or dream can ever arrive. The expansion is too fast, the distance too great. They are not just unreachable, they are untouchable. This realization reshapes the idea of the universe. We often think of the cosmos as a single, vast container, with us floating somewhere inside. But in truth, each observer has their own horizon, their own bubble of the observable. Your cosmic horizon is centered on you, just as it is centered on every other point in space. Each bubble contains a unique slice of the universe's history, each shaped by where it is and when it observes. What lies beyond our horizon may still be real. Those galaxies exist. They have stars and gravity and perhaps even civilizations, thinking their own thoughts beneath different constellations. But to us, they are like pages in a book we'll never read. Their stories unfold elsewhere, forever disconnected from our own. A parallel history, sealed in light that will never arrive. And the boundary is not just a distant shell. It is also a clock. It tells us that there is a limit to how far into the future we can be seen. Even if someone, far away, builds a telescope 1 trillion years from now, they will not see the light we send today. The future shrinks too. The horizon wraps around us from both sides, limiting what we can see and what can ever see us. In the far future, the sky will grow darker. Galaxies beyond our local group will disappear, not by fading, but by falling out of view. The universe will seem lonelier, emptier, not because it is, but because the light from beyond will have stopped arriving. A cosmic quiet will descend. The glow of creation will dim, not because it ended, but because it slipped away. And yet, within this shrinking sphere, life still stirs. We still gaze outward. We still listen, because even if the universe has a horizon, our curiosity does not. We chase the edge not to catch it, but to understand it, to honor the light that still arrives, to imagine the stories we'll never hear. Somewhere, on the other side of that invisible line, a star is being born, a planet is forming, and the light that leaves them now will travel forever and never find us, not because we turned away, but because the universe itself did. Imagine two twins, identical in every way, same eyes, same heartbeat, same laughter echoing across the kitchen table. They grow up side by side, race through childhood, dream under the same stars. But then, one of them steps aboard a spacecraft, bound for the outer edges of possibility, while the other stays on Earth. The ship accelerates to a speed just shy of light itself, and time begins to bend. Years pass for the traveler, measured by meals eaten in zero gravity, days marked by instruments, journals, memories. Eventually, the ship turns around, slowing, then hurtling back toward home. When the traveling twin finally steps off the vessel, their face is smooth, barely aged. But waiting at the launch pad is the sibling they left behind, older now, worn with the slow erosion of time, eyes lined with decades. This is the twin paradox. Not a fantasy, not science fiction, but a real and measurable consequence of relativity. And despite the name, it isn't truly a paradox at all. It's the logical outcome of how time behaves when faced with motion near the cosmic speed limit. At the heart of it lies a simple truth. Motion slows time. More precisely, the faster you move through space, the slower you move through time. Not from your own point of view, everything feels normal on the ship, but from the perspective of someone watching from a distance. For the twin on Earth, years unspool with their usual rhythm, but for the one slicing through space at a blistering pace, time is stretched, drawn out like a thread pulled taut. This isn't just a trick of perception. It's not about optical illusions or psychological impressions. It's physics. If you take two perfectly synchronized atomic clocks, machines so precise they lose less than a second over millions of years, and send one on a high-speed journey, it will return ticking behind its twin. We've done this with satellites, with jets, with particles moving in accelerators. The effect is small at the speeds we can manage now, but the principle holds. The paradox arises only when we forget the journey isn't symmetric. Both twins are not simply moving relative to one another. One stays in a single gravitational well, in a nearly unaccelerated frame of reference. The other undergoes real acceleration, leaving Earth, turning around, decelerating to return. That break in symmetry is what matters. The traveler changes direction. The traveler experiences a shift in frames. And with that change comes the cost. Less time accrued. What's strange is how normal it all feels on the ship. From the traveler's perspective, the stars streak slowly by. The interior of the cabin hums. Meals come and go. Heartbeats follow familiar rhythms. They do not feel compressed or fast-forwarded. But to an outside observer, everything aboard seems to move in. Slow motion. Clocks tick sluggishly. Movements lag. Time appears to thicken. And when the ship turns back, it must accelerate, pivoting into a new reference frame. That's the moment when simultaneity shifts. What counts is now, for the traveler jumps forward on Earth. While their own clock has moved forward only a little, the Earth's clock, from their new perspective, has leapt ahead. The math bears this out. The equations hold steady. But the feeling it conjures is one of dislocation, of returning to a world that aged without you. We often hear that time travel is impossible, and yet, here it is. Not through wormholes or fantasy, but through the relentless logic of speed and space-time. The twin who traveled did not go to the past, but they did return to the future, their own future. One where more time had passed for everyone else than for them. What does it mean to know that your experience of time is not fixed? That you could, in theory, live a shorter personal life while thousands of years unravel around you. That time is not a single river but a branching network of streams, each flowing differently depending on the terrain of motion and gravity. It means that aging itself is relative. that there is no absolute measure of time's passage, only what is measured within your frame of reference. And while these effects are tiny in our daily lives, they become profound in the extremes, near black holes, on ships that skim the edge of light, in the minds of physicists imagining journeys that might one day carry humanity beyond its cradle. There's a quiet sadness in the twin paradox, too, because while one twin may return younger, they return changed in other ways. Time may have moved more slowly for them, but they still missed what unfolded back home. Birthdays, seasons, moments that passed like waves rolling across the shore, never to be repeated. The cost of moving quickly through space is often measured in what we leave behind in time. And yet, there's wonder too, because this isn't a limitation, it's a map, a guide to how the universe weaves time into the curves of its fabric, a promise that reality is stranger and more flexible than our instincts suggest, that the future is not a single, fixed point waiting to arrive, but a landscape we shape by the paths we choose, the speeds we travel, the places we dare to go. The twin paradox reminds us that every journey is also a journey through time, that every acceleration, every curve, every loop around a star shifts the tempo of your life in subtle, beautiful ways. And in those shifts, time becomes not a constant beat, but a melody played differently for each of us, shaped by motion, memory, and the strange and silent architecture of space-time. Above your head, a silent constellation orbits the Earth, dozens of satellites circling high above the clouds. Their paths precise, their signals steady. They don't shimmer or blink like stars, and you rarely think of in them. Yet every time you check your phone's map, or navigate to a new cafe, or watch a driverless car adjust its course, you're relying on their whispers from space. These satellites tell time, nothing more and nothing less. But they must tell time perfectly down to the billionth of a second, because when you're measuring location using the speed of light, even the tiniest error stretches into miles. And time, in space, is not what we once thought it was. The global positioning system works because each satellite carries an atomic clock, a machine so exact it might drift by only a few nanoseconds over entire lifetimes. These clocks beam their time down to Earth in constant pulses, like the ticks of a galactic metronome. Your phone listens to those pulses, triangulating its position by comparing how long each signal took to arrive. Light travels about 300,000 kilometers per second, so even a tiny error, just a few millionths of a second, can throw off your location by hundreds of meters. And yet, despite the elegance of the system, there's a problem. The satellites are aging at the wrong speed. Up there, far above Earth's surface, time passes differently. The satellites are moving fast, roughly 14,000 kilometers per hour, and speed slows time down. That's special relativity. But they're also farther from Earth's center, in a weaker gravitational field, and weaker gravity speeds time up. That's general relativity. These two effects don't cancel out. In fact, they stack strangely. Due to velocity, the satellite's clocks run slightly slower, about 7 microseconds per day behind Earth-based clocks. But due to reduced gravity, their clocks also run faster by about 45 microseconds per day. Combined, the net effect is a gain of 38 microseconds every single day. Not much, perhaps, but over time, it accumulates. If left uncorrected, this error would cause GPS to drift by over 10 kilometers each day. So the solution? Every single GPS satellite is programmed with Einstein's equations. Their internal clocks are intentionally adjusted. Engineers built relativity into the hardware and software from the beginning, because without it, your phone wouldn't know where you are. Planes wouldn't stay on course. Banks couldn't timestamp transactions. Electrical grids wouldn't stay in sync. Relativity, once thought of as an abstract theory, something distant and esoteric, has become a part of your daily life. You are, in a very real way, using general and special relativity every time you get directions to the grocery store. It's strange to think that something as grand as time dilation, an idea born in thought experiments and chalkboard equations, has become embedded in the infrastructure of modern life. That the curving of space-time, the slowing of clocks, the speeding up of others, is no longer just for astronauts and physicists. It's for you, for everyone. Hidden inside the devices in your pocket, quietly calculating your position with invisible math that bends space and stretches seconds. These satellites orbit in what's called medium, Earth, orbit about 20,000 kilometers up, high enough that gravity's grip is loosened, but not so high that they drift aimlessly. They complete an orbit every 12 hours, sweeping the sky in graceful arcs. Their signals, though faint, reach every corner of the Earth, overlapping in complex patterns, allowing even a single receiver to listen to multiple at once. And with enough of those signals, your phone solves for the only point in space and time where they all intersect. That point is you. What's remarkable is how seamlessly it all works. You don't see the equations. You don't need to. But they're there, humming quietly beneath the surface, keeping your location accurate, your world mapped, your movements understood by machines. The satellites don't know where you are. They simply shout the time, and your device, listening patiently, measures those shouts against the speed of light and calculates a position that agrees with them all. It's a conversation across time, across gravity wells, across frames of reference, and it only makes sense because Einstein taught us how time flexes under motion and mass. There was once a time when these ideas were considered radical. That time could run differently depending on where you were, how fast you moved, how close you stood to a planet. That clocks could disagree not because they were broken, but because they were obeying the deep structure of the universe. But today, those ideas are hardware. Satellites must know how space-time bends. They must carry with them the shape of Earth's gravity and the memory of motion. Without relativity, GPS would fail within minutes. So the next time your map reorients, the blue dot sliding calmly into place, think of the sky above. Think of the satellites, each carrying a timepiece tuned by a century-old insight. Think of how, without ever seeing it, you're riding the curves of space-time, trusting in the same laws that govern black holes and galaxies and the edge of light itself. Einstein may never have imagined it would come to this, that his thought experiments, trains moving at light speed, clocks on mountaintops would one day make Uber arrive on time or guide lost hikers out of fog-drenched woods. But here we are. Space and time are not fixed. They never were. But we've learned how to live with that. We've built machines that understand it. And because of that, we never have to be lost. If you could shrink yourself not just to the size of a cell or an atom, but much further down, far beyond anything a microscope can see, past electrons, past quarks, down to the smallest unit the universe allows, you would find yourself in a place where the rules no longer make sense. A place where space and time, once so familiar and smooth, unravel into chaos. Where direction breaks down. Where the concept of before and after flickers. Where even the idea of location begins to dissolve. This is the Planck scale, the boundary where space-time stops being continuous and becomes something else entirely. Not a canvas, but a patchwork. Not a smooth fabric, but a foam. We're used to thinking of space and time as stable, reliable things. They stretch and bend, yes, but they do so with grace. Like a dancer, gravity curves space-time gently around stars and planets. Waves ripple through it when black holes collide. But beneath that elegance lies a more turbulent truth. At the smallest scales imaginable, around 10, -35 meters, space-time may be anything but smooth. Physicists call it quantum foam. The term was coined to capture the idea that the very structure of space-time, if magnified enough, would resemble the churning surface of an ocean caught in a storm. Waves erupt and vanish. Peaks rise and collapse. Distances fluctuate. Here, the rules of classical geometry no longer apply. Instead of coordinates and curves, you get probabilities. Instead of continuity, you get bursts of uncertainty. This foamy texture is a consequence of trying to merge two great theories. General relativity, which governs the vast and the massive, and quantum mechanics, which rules the very small. Each theory works beautifully in its own domain. But where they overlap at the beginning of the universe, inside black holes, at the Planck scale, they clash. Relativity treats space-time as smooth and curved. Quantum mechanics insists that everything fluctuates, even emptiness. In quantum physics, nothing is truly still. Even the vacuum is alive with activity. Particles appear and vanish. Energy flickers in and out of existence. And if space itself is subject to these rules, then it too must fluctuate. It cannot be a static backdrop. It must jitter, tremble, pulse with quantum uncertainty, not just in time, but in shape. The geometry of the universe, at its deepest level, may be in constant flux. Imagine trying to measure a distance between 2 points at this scale. You set your measuring rod, or whatever hypothetical tool you might use, and the distance changes before you can finish. Try again, and it changes again. Not because you made a mistake, but because the very idea of distance has become unstable. Space is no longer a stage, it's a storm. We don't yet have a full theory of quantum gravity, but hints emerge from many directions. Loop quantum gravity suggests that space itself is woven from loops, tiny, discrete threads that snap together to form volume. String theory imagines the particles and forces we observe as tiny vibrating strings, their notes shaped by the geometry of unseen dimensions. Others suggest space-time might be emergent altogether, not fundamental, but something that arises from deeper, more abstract laws, like temperature emerging from the motions of countless molecules. Whatever the truth, it's likely that space-time is not fundamental, that beneath it lies something stranger, and yet we live far above that scale. For us, space-time appears smooth, like a table that looks flat despite the atoms vibrating beneath its surface. Just as water seems calm from a plane but teems with motion beneath, so too does the cosmos conceal its foundational turbulence. The quantum foam never rises to the level of our eyes. Its dance is too fine, too quick, too deeply buried. But its consequences might echo upward. Some theories suggest that the foaminess of space-time could leave faint imprints, tiny irregularities in the light from distant galaxies, subtle distortions in gravitational waves, small deviations in the way particles behave. Experiments are underway to look for these signs. So far, none are conclusive. But the search continues, and every unanswered question points to a deeper layer of reality, still waiting to be uncovered. One implication of quantum foam is that space itself may have a smallest possible unit, a limit to how finely it can be divided. Beyond that, the concept of where ceases to apply. It's like trying to measure position in a dream. You can name a location, but it might melt away the moment you focus on it. Time may behave the same way. At the Planck scale, even now may be fuzzy, and that raises unsettling questions. If space and time are both uncertain, then what becomes of causality? What becomes of the chain of events we rely on to build meaning, to make choices, to remember? Does the universe lose its narrative thread? Or is there a deeper order beneath the chaos and invisible rhythm we've yet to decipher? Perhaps the foam is not random after all. Perhaps it hums with structure, woven with patterns too subtle to detect, too complex to yet comprehend. A kind of quantum music that, when played across eons, builds the cosmos we know. We are creatures of smooth space and ticking clocks. But the world beneath our feet, beneath our atoms, beneath our very thoughts, may not be so orderly. The foundations ripple, the geometry twitches, and reality, at its root, may be less like a map and more like a mirage, shimmering, uncertain, beautiful in its unpredictability. If we could stand at the edge of that foam and listen, perhaps we would hear the first whispers of a theory that unites the great forces. A voice speaking not in the language of matter and motion, but of information and emergence. A voice that tells us that the universe is not made of things in space-time. It is made of space-time itself. And even that is not the end of the story. In the quiet folds of deep space, where galaxies drift like lanterns and the fabric of reality stretches toward the unknown, there may exist bridges hidden, silent corridors carved into space-time itself. They don't glow, they don't spin, they don't hum with science fiction glamour. But if they exist, they are among the strangest phenomena the universe has ever hinted at. They are wormholes, and they might just change how we think about distance, connection, and time itself. A wormhole is not an object. It is not a place, either. It's a path, a shortcut through the geometry of existence. Imagine space-time as a sheet of paper. You could travel from one corner to another by sliding across the surface. But what if you could fold the paper, press those corners together, and punch a hole straight through? That hole, fleeting, narrow, and impossibly steep, would be a wormhole. A tunnel from one region of space-time to another, bypassing the long road in between. The equations of general relativity allow for such things. Einstein himself, along with his collaborator Nathan Rosen, proposed early versions of them. Einstein-Rosen bridges, mathematical solutions that hinted at tunnels connecting separate points in space or even separate universes. Later, physicists like Kip Thorne explored whether these tunnels could remain open, stable, traversable. The math, strange as it is, didn't forbid it. But there was a catch. To keep a wormhole from collapsing, something would have to hold its throat open, and not just anything, something exotic, something unlike any matter we know. It would need to have negative energy density, a substance that bends space-time in the opposite direction of normal mass. Regular matter pulls things in. Negative energy would push space itself apart, like scaffolding resisting collapse. It doesn't break the laws of physics, but it brushes close to their edge. Quantum mechanics offers a few fleeting hints. In the Casimir effect, for instance, particles can be coaxed into arrangements where negative energy briefly exists between two plates in a vacuum. It's subtle, it's temporary, but it's real. Could enough of this exotic energy be harnessed to stabilize a wormhole? Maybe. We don't know. We don't even know how to begin. Still, the idea persists. And with it, the implications begin to spiral outward. If a wormhole connected two distant points in space, then in theory, a ship could enter one side and emerge on the other, crossing light years in seconds. But there's a stranger twist. Wormholes don't just link locations, they can link moments. One entrance could age more slowly than the other, just like the traveling twin in Einstein's famous paradox. If timed correctly, stepping through could become a kind of time travel, a loop, a door to yesterday. Of course, this raises all the usual questions. Could you meet yourself? Could you send a message to the past? Could paradoxes bloom messages with no sender, causes without effects? The universe, in all its wisdom, may protect itself from such possibilities. Some physicists propose a chronology protection conjecture, the idea that the laws of physics somehow prevent time travel through wormholes from being possible, even if the equations suggest it. Could be. Others are less sure. What we do know is this: the structure of space-time is not simple. It curves and ripples. It bends around stars and caves in at black holes. And perhaps, in rare and hidden places, it loops back on itself, creating shortcuts not only through distance, but through causality. So far, we haven't seen a wormhole. No signal has passed through one. No light has emerged from a tunnel between stars. But theoretical physics doesn't require that we've observed something before we can ask what it means. It only asks that our questions stay within the realm of what is mathematically possible. And wormholes, strange as they are, remain possible. They might be born in the early universe, brief bursts of warped geometry, now lost to the cold silence of space. They might exist within the fabric of black holes, their mouths hidden beyond the event horizon, unreachable but not unimaginable. They might even be seated in the quantum foam at the Planck scale, connecting distant regions of space through tunnels so small and fleeting that no particle could ever hope to pass through. Or maybe, just maybe, they're waiting to be built. The far future of engineering, if such a thing exists, might involve not metal and motors, but the shaping of space itself. Not roads through landscapes, but roads through reality. A civilization advanced enough could, in theory, manipulate exotic matter, construct wormholes, stabilize them, and use them not to escape the universe, but to thread it together. And what would it feel like to step through such a tunnel? Would there be a flash of light, a ripple in the air? Or would it be as simple and silent as turning a corner, as uneventful as passing through a doorway you hadn't seen before? No one knows, but the equations allow for the question. The shape of reality, it turns out, might not be flat or infinite, but folded, tangled, and threaded with paths we cannot yet trace. And in that possibility lives the spark of something ancient and new, of travelers who do not cross space, but reweave it, of journeys that do not follow the stars, but leap between them. Wormholes remain theoretical, they remain elusive, but they whisper something profound. That space is not merely the distance between things, it is a structure that can be molded. And if we ever learn to mold it, the universe may open in ways we can't yet imagine. Not by going faster, but by taking a different route entirely. One hidden just beneath the surface, waiting, far above the earth, where the sky deepens into black and the air disappears. A lone astronaut floats in silence. She's surrounded by instruments and panels, wires tucked neatly behind glowing screens. But outside her window, the planet rolls past in slow, unbroken majesty. The continents drift like clouds beneath her. Oceans shimmer like spilled ink. And despite hurtling around the earth at thousands of kilometers per hour, she doesn't feel a thing. No push, no pull. Just the quiet sensation of being suspended, neither rising nor sinking. Perfect stillness, wrapped inside incredible motion. This is the paradox of freefall. On Earth, we learn early what falling feels like. It's that rush in your stomach on a roller coaster, the tug at your limbs when you trip or jump. It's acceleration, unmistakable and urgent. But in space, that feeling disappears. Not because gravity vanishes, it doesn't, but because the floor that normally pushes back is gone. There's nothing to interrupt the fall. Astronauts aboard the International Space Station are not weightless because gravity has released them. Gravity is still very much present. In fact, it's nearly as strong as it is on the surface. About 90% of Earth's pull still reaches them. What makes them float is not the absence of gravity, but the fact that they are falling with it, all the time, without end. They are in free fall, wrapped in a perfect dance around the planet. Einstein saw this clearly. He imagined an elevator in deep space, accelerating upward. Inside, you would feel pressed to the floor, just as if gravity were pulling you down. Then he imagined that same elevator falling freely through a gravitational field. Everything inside would fall at the same rate. A dropped ball wouldn't drop, it would hover. A person wouldn't feel their weight. They would float. For that moment, in that frame, gravity would vanish. It's not that gravity has stopped working, it's that everything is responding to it equally, following the same curved path through space-time. And this is the heart of it. Free fall is not the absence of gravity, it is the purest expression of it. When you stand on the ground, your body is actually resisting gravity. Your feet push against the earth, and the earth pushes back. That resistance is what creates the sensation of weight. But let go of the ground, and that sensation disappears. You're not being pushed anymore. You're simply following the natural curve of space-time, a path carved by Earth's mass. Orbiting is just another kind of falling. If you throw a ball hard enough, it travels in an arc before hitting the ground. Throw it harder, and the arc stretches further. Throw it fast enough, about 28,000 kilometers per hour, and the arc becomes the curve of the Earth itself. The ball falls, but the ground keeps curving away beneath it. This is orbit, a continuous fall that never lands. The astronaut circling the Earth isn't defying gravity. She's surrendering to it completely. Inside the spacecraft, every object is falling together. The ship, the astronaut, the floating pen, each follows the same trajectory through the same curved space-time. There's no difference in their motion, so there's no force to feel. To an observer inside, it seems like gravity has been switched off. But outside, from a larger frame, it's clear. They're all riding a curve, drawn by Earth's mass. This is why Einstein described gravity not as a force, but as geometry. Objects move the way they do because they are following the shape of the world around them. Mass bends space-time, and things fall not because they're pulled, but because they are taking the straightest possible path through that bent geometry. It's the same path you follow when you trip, or when an apple drops from a tree. The astronaut's path just happens to wrap endlessly around the planet, and in that fall, there is serenity, no jolts, no resistance. Just the continuous unfolding of a trajectory written into the structure of space itself. If you could ride that path long enough, you would come to understand something intimate about the universe, that gravity isn't a thing that happens to you. It's something you participate in. Every object with mass carves a dent in the fabric of space-time, and every other object responds, not by being yanked or tugged, but by gliding along the curvature that's already there. It's an invisible ballet, with each step choreographed by mass and motion and time. Free fall reveals that ballet. It removes the floor. It strips away the sensation of resistance and lays bare the raw geometry beneath. And there's something poetic about that. To fall endlessly without ever touching ground is to be closer to gravity than you've ever been. To feel nothing is, paradoxically, to be most aligned with the shape of the universe's pull. It's not an absence. It's a perfect agreement between you and the cosmos. Here on Earth, we rarely experience this purity. We live in the tension between gravity and resistance. Our muscles push back, our bones brace, but in orbit, that tension dissolves. There is no fight, only flow. And so the astronaut floats, watching the world turn below. She's not flying, she's not hovering, she's falling gracefully, endlessly, and with no sensation at all. And perhaps, in that stillness, she feels something we rarely do. Not detachment from the Earth, but a deeper connection to the curve of its presence. Not the absence of weight, but the full embrace of gravity's quiet geometry. To fall forever is not to be lost. It is to be in harmony with the universe. Imagine standing in a field with no edge. You walk forward, and the horizon stretches before you. You keep walking, never finding a wall, never falling off an edge. You walk far enough, long enough, and eventually, without realizing it, you return to where you started. Not because you turned around, but because space itself brought you back. This is the strange possibility that the universe, vast as it is, might loop, not in the simple way a circle does, or even the way a sphere wraps around itself, but in a deeper, subtler, four-dimensional sense. A way that doesn't require boundaries, yet still curves back on itself. A universe that is finite, but unbounded. In our everyday experience, space feels infinite. We look up at the sky and see no ceiling. We look out to the horizon and see no edge. Telescopes peer billions of light years into the past, and still the cosmos stretches further. But infinity is a tricky concept. It's not something we observe directly. It's something we assume, based on the absence of limits. But what if space doesn't stretch on forever? What if it's folded in on itself in a way we can't easily perceive, like the surface of a balloon, where every direction eventually circles back, even though there's no edge, no outside, no boundary to hit? In mathematics, such shapes are common. A two-dimensional being living on the surface of a sphere wouldn't perceive an edge. To them, the world would seem endless. But walk far enough, and they'd find themselves back where they began. The surface is closed, curved, and yet has no border. Now, imagine the same idea, but in three spatial dimensions, space curving through a higher dimension we can't access, looping back on itself in a kind of cosmic recursion. This is one model for the shape of the universe. A closed topology, a space-time that is finite in volume, yet without edge or end. A place where you could, in theory, launch a spaceship in one direction and, given enough time and patience, arrive again from the opposite side. There are other possibilities too. The universe might be a three-dimensional torus, a donut-shaped structure where space wraps around in all directions. Or it might be a more complex topology, something not easily imagined, with properties that twist and fold through abstract geometries. Shapes that mathematicians can describe, but the human mind struggles to hold. And yet, these ideas aren't just abstractions. They emerge from real questions about the nature of space-time. Einstein's general theory of relativity doesn't dictate the shape of the universe. It merely allows space to be curved by mass and energy. The global topology, whether it loops, stretches, or ends, is something the equations leave open. It's up to observation, and perhaps deeper theory, to decide. Cosmic background radiation, the afterglow of the Big Bang, offers clues. Its faint, ancient light carries imprints of the universe's shape and structure. Some scientists have searched it for repeating patterns, evidence that light has circled the cosmos more than once, intersecting itself like waves in a pool. So far, no clear evidence has emerged. But absence of proof is not proof of absence. The universe could be closed and still too large for us to notice. The light simply hasn't had time to make the full loop. And if it already has, in ways too subtle for us to yet detect, then the photons arriving at our telescopes might have passed through the same patch of space more than once, from different angles, at different times. They could be echoes of a structure too grand, too curved, for our local instruments to resolve. A looping universe also invites reflection about time. If space curves, could time as well? Could events repeat? Could history be cyclical in ways we don't yet grasp? Physics doesn't rule it out. Closed time-like curves, paths through space-time that circle back, are mathematically possible in some solutions to Einstein's equations. In those models, the future folds back into the past. Cause and effect dance in loops. The arrow of time, so constant in our daily lives, might bend under the right conditions. Of course, none of this is easy to confirm. We are creatures bound to one region of space and one moment in time. Our senses evolved to navigate flat surfaces, not curved geometries. Our brains weren't built to imagine the full shape of the cosmos. But that doesn't mean we can't try. And when we do, when we stretch our thoughts beyond the edge of what's comfortable, we find something humbling. The shape of the universe may not be infinite or empty. It may be intimate and whole. A single, seamless volume, stitched together in ways that make borders unnecessary. A cosmos with no center, no outside, no edge, just connection, endless return. a place where forward eventually becomes back again, and where the farthest reaches are never truly separate from here. We may never reach those looping paths in a spacecraft. We may never see the same galaxy twice from different angles. But the idea that we live inside a vast, curved unity has a quiet kind of poetry to it. It suggests that nothing is truly distant, that every journey is a path through something whole, that even the farthest star might, in some deep geometric sense, be your neighbor. And in that loop, silent, invisible, immense, we may find not only a model of the universe, but a reflection of something more. In the world we're used to, distance matters. A whisper fades with space. A glance only reaches so far, and no message moves faster than a signal carried through air or wire or light. Here and there feel like solid, dependable boundaries measured in meters, defined by motion. But in the quantum realm, that comfortable certainty begins to slip, and in its place grows something stranger, a connection that defies space altogether. It's called entanglement, and it may be the universe's way of hinting that separation is not as real as we think. Entanglement begins innocently enough, with particles, tiny, trembling bits of reality that become linked, not just in location, but in behavior, spin, polarization, energy, whatever properties they carry. Once entangled, they become deeply, invisibly correlated. Change one, and the other changes too, instantly, no matter how far apart they drift. Imagine two particles created together in a single moment, then sent flying in opposite directions. One heads off toward a galaxy 10 billion light-years to the east, the other to the west. Time passes, stars are born, planets die. And then, after eons, someone in one corner of the universe measures one of the particles, just a flicker of observation, a choice of how to look, and the other particle, impossibly far away, responds, not later, not soon, now. This isn't communication, nothing is sent, no signal flies through space, but something deeper happens, a ripple not through the air or vacuum, but through the very structure of correlation. It's as if the universe, at its most fundamental level, knows these two particles are linked, and that knowledge cannot be broken by distance. Einstein famously called it spooky action at a distance. He couldn't believe the universe would allow such a thing. To him, reality had to be local, that what happened here could only be influenced by things nearby. But quantum mechanics stubbornly refused to cooperate. Experiment after experiment confirmed it. Entangled particles behave as if distance doesn't exist, as if space, in some hidden way, is an illusion. And that's where things get strange, because space-time is supposed to be the stage on which everything happens. It's the thread that connects one moment to the next, one object to another. It gives us here and there, before and after. But entanglement suggests that this stage may not be fundamental, that under it lies something deeper, something that doesn't care about distance at all. In this deeper realm, location isn't fixed by coordinates, it's defined by relationships, and what we call space might emerge from those relationships, not the other way around. Two particles aren't connected because they're close in space. They are close in space because they are connected. It's a reversal so profound it scrambles our intuition, but it's a view that's gaining ground. Some physicists now believe that entanglement isn't just a feature of quantum theory, it's the foundation of everything. That space itself, and even time, may be built from webs of quantum entanglement. In this vision, space-time is not smooth or continuous. It's woven, stitched together by threads of connection between quantum bits, like a hologram whose three-dimensional shape emerges from a lower-dimensional network of information. Geometry, gravity, even black holes, they may all be shadows cast by deeper patterns of entanglement. And if that's true, then the real architecture of the universe isn't made of points in space. It's made of connections. This idea shakes more than physics. It touches the way we think about identity and separation, about what it means to be part of a universe that is not stitched together by emptiness, but by entangled, invisible threads. If here and there are illusions born from the web of relationships, then maybe self and other are too. Maybe we are more entangled with the world than we imagine. In the lab, we can only scratch the surface. We can entangle photons, atoms, even small groups of molecules. We can measure their correlations, predict their outcomes, marvel at how perfectly they defy classical expectation. But what lies beneath the mechanism, the reason, the source of this deep non-locality remains hidden. Some think entanglement points toward a quantum theory of gravity, where information, not force, is the true glue of the cosmos. Others wonder whether entanglement could allow for teleportation of information or even matter across space, though always bounded by the rules that keep causality intact. No faster than light messaging, no paradoxes, just the subtle rearrangement of quantum structure like folds in a fabric we cannot yet see. And yet, even without full understanding, we've begun to use entanglement. In quantum computing, it allows calculations that explode in complexity. In cryptography, it enables security that can't be broken by any eavesdropper. And in philosophy, it forces us to confront what it really means to be separate. Because at the smallest scale, the universe doesn't seem to believe in separation. It believes in relationship, in interdependence, in the quiet truth that what happens to one part of the cosmos may always ripple through the rest, not by traveling, but by being. Not through force, but through connection. Entanglement doesn't erase space, but it hints that space, as we know it, may be only a projection of something deeper. A language of positions and directions mapped onto a world where what really matters is who shares what, and how deeply. And perhaps, in that web of invisible threads, we'll one day find a new picture of reality, one where distance is not about meters or miles, but about meaning. One where the universe isn't built from parts moving through space, but from moments bound together, entangled beyond time. Light doesn't just travel, it remembers. Every beam that strikes your eye from the night sky carries not only illumination but age. When we look up at stars, we're looking into the past. Not metaphorically, but literally. The light we see has taken years, centuries, even eons to arrive. And in that light is a story, stretched across the deep fabric of space and time. But sometimes, the universe gives us more than a single glimpse. It bends the path of light, folds the distance, and offers multiple versions of the same moment staggered across time. Through an elegant distortion known as gravitational lensing, we are granted the impossible, to see one object not once, but many times, separated not by space, but by history. This isn't science fiction. It's a real, observed phenomenon, and it begins with mass. Massive objects, galaxies, clusters of galaxies, even dark matter halos warp space-time itself. They don't just sit in space, they shape it. Their mass pulls on the geometry of the cosmos, creating invisible valleys and ridges in the gravitational landscape. And when light from something distant passes near these deformations, it doesn't travel in a straight line anymore. It bends, curves, splits. It becomes a message written in echoes. Imagine a distant galaxy, so far that its light has been streaming toward us for billions of years. Between us and it, a massive galaxy cluster drifts silent and dark, invisible to the eye, but immense enough to twist space like a spoon in honey. As the light from the far-off galaxy reaches this warped region, its path is curved. Some rays bend slightly, others sharply. Some loop around, arriving at Earth from a different angle entirely. By the time that ancient light reaches our telescopes, it may appear not as a single dot, but as arcs, halos, or even multiple images, each a copy of the same object, arriving at different times. In some cases, the delays between these light paths are tiny, days, weeks, maybe months. But sometimes, the detour is vast, like a car taking the long road around a mountain. One image may arrive now, another, centuries later, and still another might have arrived long before we had eyes or instruments to see it. Each image is a window into a different moment of the same event. One of the most dramatic examples was seen in 2014, when astronomers observed the explosion of a distant star, a supernova named Restful. Because the light had passed through a gravitational lens, it split. The same explosion appeared multiple times in the sky, like ghostly repetitions of a single, colossal death. One version of the supernova appeared months after another, even though both came from the same event. The universe, through nothing more than mass and geometry, had created a time machine. What's remarkable is that these aren't illusions. They're not tricks of optics or chance reflections. They are real photons, taking real paths, bent by real curvature. The universe is doing the lensing, not glass, not mirrors, but the structure of space itself. This means we can use gravitational lenses to peer deeper than ever before. They magnify faint, distant galaxies that would otherwise be too dim to detect. They stretch ancient light, revealing details about the early universe. In a sense, these lenses act like cosmic telescopes built not by engineers, but by gravity and chance alignment. But they're more than magnifiers. They're archives. Because light travels at a fixed speed, the further away something is, the older its light. And when that light is bent, delayed, and split, we're given more than just one version of the past. We're handed fragments of time staggered, layered, replayed. Imagine watching a movie, but instead of seeing it once from beginning to end, you receive pieces of it out of order. One scene arrives early, another, months later, and another hasn't come yet, but you know it will. You can predict it because the lensing geometry tells you when to look. That's exactly what happened with Restful. Astronomers used the lensing model to forecast when and where the next image of the supernova would appear. They turned their telescopes to the predicted spot, and there it was, light from a star that had died long ago, finally reaching Earth again through a different cosmic corridor. This predictive power is more than a curiosity. It helps refine our understanding of dark matter, which influences how light bends but remains unseen. It tests our models of space-time, confirms the reliability of general relativity, and even offers a potential route for studying the expansion of the universe. But there's something deeper too, something harder to quantify. Because gravitational lensing reveals not just the shape of space, but the pliability of time. It shows us that the past is not buried, it's traveling, carried by light, delayed by curvature, waiting patiently to arrive. And sometimes, if conditions are right, we get to witness an event again. The same supernova, from a different path. The same galaxy, seen through a different century. We begin to realize that time in the cosmos is not a river, flowing evenly forward. It is a vast, branching delta, where light meanders and loops, where echoes arrive long after the shout, and where memory is not stored in minds but in beams of starlight crossing space. Through these natural time machines, we learn that the universe is not a fixed tableau. It is alive with delay, recursion, and replay. We are not just observers, but receivers of layered moments, pieced together from scattered photons. And somewhere out there, light is still on its way, carving a path through bent space, slowed by gravity, whispering of events long gone, carrying futures that are also past. And one night, it will arrive, and when it does, we'll look up and see the same star die again. Time has a direction. At least, that's how it feels to us. Milk spills but never unspills. Ashes don't leap back into logs. You grow older, never younger. Moments slip behind us like footsteps fading into the dark, and no matter how much we want to, we can't walk backward into yesterday. It seems obvious, unchangeable, but the deeper we look, the stranger it becomes because the laws of physics don't actually prefer a direction. On paper, equations work just as well in reverse. A falling glass and a rising one are equally valid. A film rewound makes no less sense than one played forward. And yet, here we are, trapped in a stream that flows only one way. This is the arrow of time, the idea that time isn't just a measurement of change, but that it moves, with a before and after, a beginning and an end. And the question is, why? The answer, or at least the best one we found, lies in a single word: entropy. Entropy is a measure of disorder. It counts the number of possible arrangements a system can have, the ways things can be shuffled, jumbled, spread out. And the second law of thermodynamics tells us that entropy tends to increase. Left to itself, the universe drifts toward chaos. Ice melts, ink spreads in water, the smoke doesn't return to the match. Each of these transformations is not forbidden in reverse, but they're overwhelmingly unlikely, because there are so many more ways for things to be disordered than ordered. A neat stack of cards can be arranged in only one perfect sequence, but a shuffled deck? There are trillions upon trillions of possibilities. The odds that random motion would return it to that one neat order are so small, you could wait longer than the age of the universe and never see it happen. This is why time feels like it flows forward. Because entropy increases. The past is the low entropy state, the rare beginning where order was high. The future is the high entropy sprawl, where differences fade and energy disperses. Memory, too, is tied to this imbalance, We remember the past because information from it remains structured, light, impressions, imprints in our brains. But the future hasn't left such footprints. Not yet. This arrow of time isn't built into the fundamental rules. It emerges from conditions, from the fact that, for reasons still not fully understood, the universe began in an extraordinarily low entropy state. Smooth, even, compact. A moment of immense potential. And from there, the unfolding began. Galaxies formed not in spite of entropy, but because of it. Gravity, in its counterintuitive way, creates structure as it increases entropy. Clumps collapse, stars ignite. And over time, as heat spreads and energy balances out, the universe will settle into a quieter state, one where change becomes rare, and time itself may lose its meaning. But is this direction final? Could the arrow of time ever reverse? In theory, if entropy were to decrease, if the universe somehow moved toward more order, then the arrow would flip. The future would become more like the past. Clocks would still tick, but their hands would spin backward. A glass might unshatter, a life might untangle. But this reversal would require an extraordinary change, a boundary condition so exotic and precise that it borders on impossibility. Not because the laws forbid it, but because the probabilities become vanishingly small. To see time reverse, you'd need to wind the entire universe back into a lower entropy state. Every atom, every photon, every particle rearranged. And yet, some interpretations suggest it could happen not here, but elsewhere. In the distant future of a contracting universe, if the cosmos were to collapse back on itself, perhaps entropy would begin to flow the other way. In that case, the beings on that side of the bounce might feel their own time moving forward, while to us, it would look like they were moving backward. It's hard to say. Harder still to test, because we live inside the flow. We're part of it. Our thoughts, our breath, the ticking of our hearts, all shaped by entropy's march. We don't see time as reversible because we aren't. Memory, biology, decay, all of them ride the current. Still, hints of timelessness exist. In the quantum realm, particles don't obey a strict forward sequence. Some processes seem to ignore direction altogether. And in the equations of relativity, time is just another coordinate, like space, a dimension to be traveled in theory in any direction. So maybe time, as we feel it, is a kind of illusion, not false, but emergent like temperature or color, a product of motion and difference, not a fundamental quality of the universe. Maybe time isn't a thing at all, but a story we tell ourselves, drawn from the unfolding of entropy around us. And if that's true, then what we call now is just a point on a much larger map, one that doesn't care which way we face. Still, there's something beautiful in the arrow, even if it's only a statistical preference. It's what makes life possible. What gives meaning to memory, to anticipation, to growth and change? Without it, we'd be frozen. A still life of possibilities, unplayed. Time moves forward, not because it must, but because it's the likeliest path. And we brief, flickering creatures of pattern and thought ride that path like a wave, watching as the past fades, the present burns, and the future beckons with every breath we take. Before the first stars burned, before galaxies spiraled into form, before atoms danced or light stretched itself across the void, there was no before. Not in any sense we can hold in our hands, not in the way you remember yesterday or anticipate tomorrow, because time, the very thing that lets one moment follow another, did not exist. It had not yet begun. And this is the quiet, impossible truth at the heart of everything. The universe, in all its vastness, didn't erupt into space and time. It brought them with it. The Big Bang isn't just the beginning of matter or light or heat. It is the beginning of when, the birth of where. Every clock, every orbit, every heartbeat all trace their lineage back to a moment not of explosion, but of emergence. An unfolding not into something, but as something. Not a fireball expanding through a pre-existing stage, but the stage itself blooming outward, carrying every actor, every line of the script, every possibility. Try to picture it, and the mind recoils. What does it mean for time to start? How can there be a first moment if there's nothing before it? Our instincts lean on metaphors, fireworks, bursts, bangs, but they betray us. Because this wasn't a bang in space. It was space. It wasn't something that happened at a location. It was the arrival of location. It wasn't somewhere in the universe. It was the universe. Roughly 13.8 billion years ago, in less than a fraction of a blink, something happened, not in time, but to time. A point of infinite density and a temperature, or something stranger still, where the known laws of physics melt like ice in fire. A singularity, some call it, but even that word stretches meaning. It is less an object than a boundary, less a place than a limit on what questions can even be asked. Because to ask what came before the Big Bang is like asking what's north of the North Pole. The idea is nonsensical not because it's forbidden, but because it's meaningless. Time, as we know it, is threaded into the very fabric of the universe. It is not something outside the cosmos, watching from the wings. It is part of the show. And in those earliest moments, if we can even call them that, the universe didn't resemble anything familiar. There were no stars, no planets, no empty space, just an expanding fog of energy, dense and hot beyond imagination. Particles winked into being, collided, annihilated, and reformed in a blur of pure physics. Space was tiny and curved and trembling, like a note, just beginning to be sung. Time, fresh and fragile, ticked forward, one breath at a time. Yet out of this chaos, order began to crystallize. As expansion continued, the universe cooled, forces separated from one another, gravity unfurling from the others, like threads being teased apart. Matter found a way to endure. Atoms formed, light decoupled, and with each change, the geometry of space shifted, grew, and softened. In time, billions of years later, stars would ignite, galaxies would swirl, and planets would cradle oceans and forests, and people who would one day look up and ask, how did it all begin? But the deeper we look into that question, the more it humbles us. Because the Big Bang wasn't just the start of a thing, it was the birth of a canvas upon which all things could be painted. Space-time isn't the backdrop to the play, it is the play. Every particle, every beam of light, every tick of a clock is a ripple in that fabric. This idea that the universe began with time itself is not just poetic. It is what the equations tell us. General relativity, Einstein's great gift to our understanding of gravity and geometry, describes time not as an external tick, but as a property of the cosmos. The ticking slows near massive objects. It stretches when we move fast. It flows only because entropy increases. It bends and warps and follows the same rules as space. And so, when we talk about the Big Bang, we are not talking about a place in space that exploded. We are talking about the birth of dimensionality, the blooming of causality, the unfolding of a universe where distance and duration could begin to mean something at all. There may be deeper truths still. Some cosmologists propose that our Big Bang was just one in an eternal sequence, that perhaps there was a before, but not in terms we yet understand. A previous universe contracting, bouncing, birthing ours in its death. Others imagine a multiverse where our cosmos is one bubble in a frothing sea of inflating space, each bubble with its own time, its own laws, its own birth. These ideas are wild, mathematical, and difficult to test, but they share one trait. They stretch the imagination beyond its comfortable boundaries. Still, even if such ideas are true, they only push the question one step further. Why this universe? Why this structure, these laws, this beautiful unfolding? We may never know, but perhaps that's the point. Not all mysteries are meant to be solved. Some are meant to be held, to be sat with, to be whispered to as the stars wheel overhead. The Big Bang is not just a scientific theory. It is a lullaby written in cosmic language, telling us where we come from, even if we don't fully understand the tune. Because in the end, we are all children of that first breath. Our atoms forged from its aftermath. Our moments strung like pearls on the thread of its time. Our lives brief, flickering sparks, and yet deeply, intimately connected to the first spark of all. The moment when not just everything began, but when anything could. Out at the furthest edges of understanding, where the maps go blank and the equations lose their footing, we reach a place where the very idea of place begins to dissolve. A frontier, not of distant stars or hidden galaxies, but of meaning itself, where the familiar scaffolding of space and time buckles, blurs, and falls away. It's here, in the trembling overlap between general relativity and quantum mechanics, that we find ourselves staring into the great unknown, not beyond the stars, but beyond structure, beyond even the fabric that holds reality together. Space-time has carried us far. It has shaped the orbits of moons and the slow drift of continents. It has cradled galaxies and curved under the weight of black holes. We have learned to measure it, bend it, even listen as it ripples with the passing of distant collisions. It feels foundational, the stage upon which the universe performs. But it might not be the final stage. It might not be the whole of the story, because when we try to press Einstein's smooth, continuous universe up against the jittering, probabilistic world of quantum physics, something cracks. Relativity says space-time is a seamless fabric, bent by mass and energy. Quantum mechanics says everything is uncertain, flickering, probabilistic. Even empty space is alive with ghostly fluctuations. For nearly a century, these two theories have resisted reconciliation. They speak in different languages. They measure in different rhythms. They imagine reality in incompatible ways. And yet, we know they must meet. Somewhere, deep down, they are looking at the same truth, just from different sides of the veil. This meeting likely happens at the smallest scales imaginable, down near the Planck length, a distance so tiny it defies visualization, a billionth of a billionth of a billionth of a centimeter. At this depth, the smooth curves of Einstein's geometry give way to chaos. Space-time itself may begin to tremble, bubble, and fragment into something else entirely, not a continuous surface, but a foamy, flickering storm of probabilities. This is the realm of quantum gravity, a place where loops and strings and unknown ingredients may be woven together in patterns we've only begun to guess at. Some theories, like loop quantum gravity, suggest space is quantized, made of discrete units, like atoms of volume. Others, like string theory, propose that the true foundation of reality lies not in points or curves, but in tiny vibrating strands that hum the laws of physics into being. In some versions of these ideas, even time may not be fundamental. It might emerge from deeper, stranger processes, the way waves emerge from water. If that's true, then time isn't ticking everywhere. It's growing. And space? It may not be the backdrop of reality, but a side effect of something more elemental, something relational, something built not of distances and directions, but of interactions, of entanglements, of patterns of information we don't yet know how to describe. What lies beyond space-time might not be farther away. It might be deeper within, folded into every particle, hidden in the spaces between events, whispered in the statistical symmetries of the universe. And yet, this is not emptiness. It is potential. The same potential that once birthed the cosmos, that once, long ago, unfolded into hydrogen and helium, into stars and oceans, into thoughts and dreams and people who wonder where they came from. The boundary of space-time isn't the end of something. It's the beginning of something else. A question that can't yet be answered. A song not yet written. A language still forming in the silence between theories. We've seen hints. Black holes, with their paradoxes and puzzles, suggest that information, the raw currency of reality, might be more fundamental than matter or motion. That space can be shaped, not by what exists, but by what is known. Some physicists imagine reality as a vast computation, a kind of unfolding logic. In this view, the universe isn't just made of particles and fields, but of code quantum bits dancing in vast, invisible circuits. Others look to the holographic principle, the strange idea that the universe, with all its depth and dimensionality, might actually be encoded on a distant boundary, like a 3D world projected from a 2D surface. If that's true, then space-time as we experience it is a kind of illusion, a powerful, persistent one, but an illusion nonetheless. In all of these visions, one theme echoes again and again. Reality is not what it seems. It is stranger, softer, less solid. The deeper we look, the more the ground gives way. The closer we get to truth, the more it slips sideways, revealing new questions, new possibilities, new frontiers. So what lies beyond space-time? Maybe nothing, maybe everything, maybe something we don't yet have the senses to feel or the math to see. But what we do have is this, the ability to wonder, the audacity to ask, the quiet courage to look up, to peer inward, and to imagine more. And maybe that's enough, because in the end, we are not separate from this unfolding. We are its product, its witness, its question, dreaming of its own answer. We are made of space-time, yes, but also of what lies beyond.